Today we are going to discuss some numerical problems on quantum mechanics. The question is given: an electron of mass 9.11 into 10 to the power minus 31 kg is moving in one-dimensional infinitely deep potential well of width 1 angstrom. Find the ground state energy, the energy of the first excited state, and the frequency of emitted radiation due to transition of the electron from the first excited state to the ground state. According to the question, an infinitely deep potential well has been drawn here. Its width is L, and for a particle moving inside an infinitely deep one-dimensional potential box, the condition is given Vx equal to 0, the potential is 0, where between 0 and L, that is in between the potential well, the potential Vx of the particle is 0 and it is infinite otherwise. By solving the Schrodinger equation, we have obtained the expression of energy of a particle moving inside an infinitely deep potential well, which is given by En is equal to n square h square by 8 ml square. N designating the particular state where the particle is located, h being the Planck constant, m is the mass of the particle, and L is the width of the potential well. So the first part of the problem can be easily solved by just using the formula of energy given, E equal to n square h square by 8 ml square, where for the ground state we know that n is 1 for the ground state, and the value of the mass of electron is given by 9.11 into 10 to the power minus 31 kg. The width of the potential well is given by 1 angstrom, that is 10 to the power minus 10 meter, and the Planck constant is given by 6.63 into 10 to the power minus 34 joule second. So all are in same unit. If I put back all these values in the expression of energy with n equal to 1, that is the ground state, we get U1. Just putting all these value, we get U1 is 0.6 into 10 to the power minus 17 joule. Now keep in mind, if we want to obtain the value in electron volt, so just we know 1 electron volt is 1.6 into 10 to the power minus 19 joule. So by dividing this through 1.6 into 10 to the power minus 19 joule, we get answer in electron volt, that is 37.73 electron volt. The second part of the problem, that is the energy of the first excited state, can also be just obtained using the formula of energy E is equal to n square h square by 8 ml square. Now we have to use n equal to 2 for the first excited state. But keep in mind that in case of potential well problem, we already know that the energy of the second excited state, that is E2, is 4 times the energy of the ground state, that is E1, that is E2 is equal to 4 E1. So we already have calculated the value of E1. By substituting the value of E1 here, we get the energy of the second state, that is the first excited state, with n equal to 2 is 150.95 in electron volt. And if we wish to obtain the value in joule, just multiply it with 1.6 into 10 to the power minus 19, because we know that 1 EV is 1.6 into 10 to the power minus 19 joule. So the answer will be in joule. Otherwise it is in 150.95 EV. Already we have solved the first two part of the problem. The third part, which want to obtain the value of the frequency of the electron moving from the first excited to the ground state, that is from n equal to 2 n equal to 1, as shown in the right hand side with the diagram. The transition takes place from n equal to 2 to n equal to 1 state, and we already have calculated that the energy of the first excited state with n equal to 2, that is E2, is 150.95 electron volt, and energy of the ground state, which has also been calculated, that is 37.73 electron volt. So we know from the our earlier formula, that is H nu is E2 minus E1, that is the energy difference between the first two states, and we know E2 is equal to 4 E1. So just if I take the difference, that is 3 E1, which is nothing equal to H nu, the Planck constant multiplied by the frequency. But keep in mind that it is in electron volt, 113.22 electron volts. So convert it to joule, that is we have to multiply it with frequency to obtain the frequency. 1.6 into 10 to the power minus 19 into 113.22 Now it is in joule and divided by the Planck constant, that is 6.63 into 10 to the power minus 34, and the value of frequency has been obtained. Of the transition frequency is 27.3 into 10 to the power 15 Hertz. Now there is another problem of the same topic, which states that what will be the change in the ground state energy of a particle moving inside an infinitely deep potential well if the width of the well is doubled. So already we know the expression of energy for a particle moving inside the potential well. So what happens to its energy, we have to find out if the width of the well is doubled. That means keeping all the other parameters fixed, we are just doubling the width of the well. So what happens to the energy of this particle? So already we know the expression of energy of a particle moving inside an infinitely deep potential well is E suffix n square h square by 8 ml square, where h is the Planck constant, m is the mass of the particle, and l is the width of the well. Here n designates the particular state. Now as per the given condition, what happens, just keeping all the parameters same, we have just doubled the width of the potential. That means we have, if the changed length of the potential well or the width is L prime is nothing but is 2L if L is the initial width. So now what happens to the energy, just L is multiplied by 2, that En is n square h square by 8 ml square, then En prime will be n square h square by 8 ml m into 2L square, that is 4L square. So if I divide them, En prime by n, it is 1 by 4. So just energy decreases compared to the initial energy by 4 times.